In this lesson, we're going to talk about storage spaces. Multi-terabyte hard disk drives are becoming increasingly common, but even though we have all this disk space available to us, we're still running out of storage space. The problem is that as the overall size of our storage device has increased, so has the amount of stuff we're storing on those disks. And most of this is due to an explosion in the type of information we're storing on our hard disk drives. 10 years ago, we primarily stored document files, email files, and things like that. Today, we store media files, music, videos, and so on. These types of files consume dramatically more space than the document files we stored 10 years ago. Storage spaces offer a new way to manage storage space on a Windows system. It makes it very easy to add disk space to a Windows system. Using storage spaces, we can take all of the storage devices in the system and pool all of the available space on those devices together. This is very useful because if we run into a situation where we're running out of disk space, all we have to do is add an additional disk to the system, and then add its free space to the storage pool. Then Windows automatically adds the new free space from the new device to our existing storage. We don't have to keep track of what data is stored on which drive. We also don't have to worry about resizing volumes. All the space is added, and you see one big drive where you can store your information. Now, if you've ever worked with Linux systems and used Logical Volume Manager to manage storage space on Linux, then the concepts we're going to talk about here are going to be quite familiar to you. Storage spaces on Windows is composed of three key components. First, we have our storage devices represented by these three different hard drives over here. We can use storage space from a variety of different storage devices. It doesn't matter if they're SATA drives or external hard drives. You can use whatever storage devices that you have on your system, and they don't all have to be the same type. We take all of the available storage space on these various devices and we pool them together into a storage pool. The pool is a logical concept. It's not a physical device. It's a logical concept that is composed of all the free space available on these storage devices that we specify. Now we can take this pool of available storage space and define individual storage spaces as identified by these volumes down here. We can take the pool and create one storage space out of it. Or we can define multiple storage spaces, each drawing space from the same storage pool. The key thing to remember is that as far as the Windows operating system itself is concerned, and the end user for that matter, these just look like disk drives in the system, logical disks. So this could be the E drive and this could be the F drive. We'd have two logical drives defined that are really storage spaces, but they're composed of space from three separate hard disk drives. The space from these drives is pooled together and then allocated to a specific storage space. Now, using storage spaces over traditional storage options has a lot of benefits. The key among these is the fact that if you start to run out of free space in any given storage space that you've defined, all you have to do is go out and buy a new storage device, like a new SATA hard disk drive, install it in the system, add the free space on that new device to your existing pool, and then allocate that new space to one of your existing storage spaces. And that's it. The space is available. You don't have to repartition anything. You don't have to resize any volumes. You don't have to back up any data and restore it. It makes things a lot easier. Another key benefit is that storage spaces include a degree of data resiliency. We have several different options for how that data resiliency is going to work, and you can see that in the screenshot here. Notice that the first option is called Simple, which, as its name implies, doesn't have any resiliency. In this situation, you would create a simple storage space by simply allocating space from a storage pool to the storage space, and there's no redundancy involved. This is dangerous because if one of your hard disk drives were to fail, then you would lose all of the data on the entire storage space. To prevent this, Storage Spaces offers several resiliency options to make your files redundant so that if a disk fails, you won't lose any data, and you can see those here. We have a two-way mirror, three-way mirror, and parity. Be aware that using one of these resiliency options will require you to allocate some space for the redundant information. In other words, it'll reduce the amount of space available for just data storage, but it's worth it because your data is much safer. Let's take a look at what each of these three data resiliency options offer, beginning with two-way mirroring. Two-way mirroring requires at least two physical disks because two-way mirroring places a copy of the data saved in the storage space on both drives, so that if one of the drives dies, the other one can still provide the data that was stored on the other one. Another option is three-way mirroring. Three-way mirroring is much more complex than two-way mirroring. Three-way mirroring requires at least 5 hard disk drives. Three-way mirroring will store a copy of each file stored in the storage space on 3 of the 5 hard disk drives. This gives you a lot less usable space than two-way mirroring does, but It provides more safety because it can tolerate the failure of up to 2 disks at the same time. So, with two-way mirroring, we can tolerate 1 disk failing. With three-way mirroring, we can tolerate up to 2 disks failing at the same time. The third option for data resiliency in a storage space is parity. Parity is similar in a lot of ways to RAID 5. Parity requires that you have at least 3 hard disk drives, and as its name implies, it uses parity information so that if one of the disks fails, the data can be reconstructed using the parity information, and this has a couple of advantages. The key among these is the fact that it uses less physical space on each disk, providing you more storage space for your actual data. But that comes at a cost in terms of performance overhead, meaning that it's not going to perform as fast as one of your other mirroring options. For example, if you wanted to define a 100 gigabyte storage space and use two-way mirroring to provide resiliency, we would have to install 200 gigabytes of physical disk space in the system. By way of comparison, if we wanted to define the same 100 gigabyte storage space using parity in the system, we would only have to have about 150 gigabytes of physical disk space. All of the different resiliency strategies that we've talked about, two-way mirroring, three-way mirroring, and parity, will store data on the drives in 256 megabyte chunks. Now, suppose we have a storage space that's configured using two-way mirroring. In this situation, a redundant copy of each 256 megabyte chunk is stored on both disks in the storage space, so that if one of the disks goes down, no user data will be lost. It's still available on the second disk. If you add new disks to the pool, the original disk from the pool will fill up that new disk with all of the different 256 megabyte chunks that it has in order to push the redundancy over onto the new disk installed in the system. The key thing to remember is that adding new disks to the pool does not affect the resiliency. All the information is copied over to the new disk so that resiliency is preserved. And that's really nice because if one of the original disks on a system dies, that redundant information is already copied over to any new disk you add to the pool. And the process for doing this is easy enough that most end users can handle it without a lot of training. Another key benefit provided by storage spaces is thin provisioning. Sometimes it's called overbooking. The idea here is that when you create a new storage space, you can actually set the size of that storage space to a value that's actually bigger than the amount of physical storage space in the pool. It does this by thin provisioning, meaning that if we assign a size to one particular storage space, like this one, the physical storage is not really assigned to that storage space. For example, let's suppose that I have 10 different users who use the same system, and I want to allocate 100 gigabytes of storage space for each of them. Your first inclination might be to say, well, I want to define a storage space of 100 gigabytes per user, and there are 10 users. Therefore, I'm going to need a storage pool that is 1 terabyte in size, right? Not necessarily, because we know in all likelihood that not all of those users are going to consume all of their 100 gigabytes of storage space. In fact, most likely, they're only going to consume a fraction of that space. Some users will use all 100 gigabytes, some of the users will not. Therefore, storage spaces actually allows us to create multiple storage spaces whose sum total size is larger than the storage pool itself. In this example, we can create 10 100 gigabyte storage spaces from a 500 gigabyte storage pool. With that said, you still have to be careful about using too little physical disk space or too many storage spaces. Because if the storage space really does run out of physical disk space in the pool, it'll immediately unmount, and if you had some type of file I/O operation going on at the time, like a save or a copy, it'll be immediately cut off and you will end up with data corruption. If this happens, you can remount the storage space manually and you can still access your files in the storage space. However, you won't be able to do much with the storage space until you add more physical disk space to the pool and allocate it to that storage space. In this lesson, we talked about storage spaces. We talked about how storage spaces manages storage spaces. We also identified the 3 key components in a storage space. And then we talked about thin provisioning, which allows us to allocate more space than we actually have physical disk space for.